Hello, my good friends. I'm back. Frazier Nyasulo is back. Let's talk Lab 7. This is Chem 1510, Lab 7. Gas laws. Oh, let's see if we've got our system slideshow. Okay. And all right, so gas laws. We're doing a number of things. Verify Boyle's law. We found it, so we can only verify it and make sure it works. Next one is kind of a strange name. Finally fixed it. In the manual elsewhere it might say verify Charles's law. Not correct. It's verify Monters Law. Monters. Verify it, and then it has its goodies. The goodies that come from that via extrapolation is a determination of absolute zero. And then we are going to determine the Henry's law constant for carbon dioxide. All right, let's start with the mother of all gas laws. The mother. Well, PV is equal to nRT. You know this scoop. That's the mother. Gotta remember volume in liters, T, temperature in Kelvin, N in moles, and pressure in atmosphere. All right, you all know all of that. Let's derive the sub-laws from the ideal gas law. How about if in the ideal gas law, as you can see here, see if I have a pen here, I don't know. Yeah, screen options, oh come on, pointer options, yeah, let's go. All right, so if in the good old ideal gas law here, we keep N and T constant, N and T constant. So if these are constant, then PV is equal to N or T is a constant. Yeah. That happens to be Boyle's law. Another way of saying that is that pressure and volume are inversely related. All right. So in our case, we're going to do that and show that if you start with a fixed number of moles and you maintain the temperature the same in any combination for a given system, pressure times volume will show that it's a constant. By doing so, we'll have verified Boyle's law. And then we'll add some questions that kind of stretch your brain and make it work. And yeah, that's the plan. How about Monters Law? How about if we keep the volume constant? So we keep the volume constant and number of moles constant. And then if we move the T to the other side by dividing by T, P over T is equal to a constant. Another way of saying it is P is directly proportional to the temperature. So we'll verify that via experimentation. So, Boyle's law, we want to show that P times V is equal to a constant using tools in our lab. So, in our case, here's a scoop. We're going to, okay. There it is. Chemistry sensor. You've used this one before, right? And up here is a pressure port. And we'll connect this to the pressure port. Got nice and gentle with it, push it in. And then when you push it in, you turn it a little, and you'll hear a little click. Did you get that? I don't know. Anyway, so that's our pressure measuring device. We'll connect it to a syringe. Syringe. And then we'll control the volume and measure the pressure. In our case, in kilopascals. A Pascal is the SI unit for pressure. Newton per meter squared is a Pascal. Just connect them. You'll have a fixed moles of gas inside. The temperature, unless you're really pumping it, the temperature should remain the same. And then you change the volume by holding down the syringe. Hold it steady, and then read the pressure, and then you have the pressure and volume combo. And then you will show that P times V is a constant within experimental error. So we'll ask you to calculate the mean and the standard deviation, and then your argument is the standard deviation is just so small, and so this is reproducible stuff. Life is good when you have the right tools to work with. Moving right on. I've already described that. All right. Now, to introduce this, let's reference Charles's law, because that's what is in your textbook anyway. So, in this case, V is directly proportional to T, or V divided by T is equal to a constant. What happens when you take a volume of, a gas, you change the temperature and you allow the volume to vary? So you're controlling the temperature and the volume is varying. What happens? Well, if you did that, maybe you could do it with a syringe. If this were really kind of movable, you could control fixed number of moles, you could control the temperature in here, and then as you warmed up, as you might guess, this would go up a little, right. So you could use this. If it were not very stuck, of course it's stuck. All right, so experimentally you've seen this plot, volume versus temperature for a gas around room temperature and above, slightly above and below, and then you end up with this, and then you say, wow, okay, volume versus temperature. This is in degrees centigrade this time. If you extrapolate the power of extrapolation, you go way down there. That is, you extrapolate to the point where the pressure is 0. Oh, in this case, sorry. In this case, the volume is 0. And then, lo and behold, you will find that in this case, it's minus 273.13. But here's the story. Here's the crux of the story. If I now move my axis and call this the 0, call this 0, then volume is directly proportional to temperature, because proportionality means you plot the data, it must be linear, and it must go through the 0 point. So volume is directly proportional to temperature only if you're using the Kelvin scale. Life is good. Let's move on. Extrapolation. All right, so now Monters, my good friend Monters. Have you talked to Monters lately? Anyway, determination of absolute 0. So what we're going to do is keep the number of moles the same, keep the volume the same. We're going to change the temperature and measure the pressure. Absolute sphere. Here's a thing that will connect to a temperature sensor. I can't get it right. It's challenging. It's like a mirror thing. Yeah, there we go. Connect that to the pressure sensor, temperature sensor. The sensors are in here. Fixed volume. And when we click it to the pressure sensor, there'll be a fixed number of moles. Then we'll put this in the temperature bath and warm it slightly, slowly that is, and measure how temperature affects the pressure. And then, what will happen? What do we expect? Here's what we expect. I'm plotting P versus T, and this happens to be degrees centigrade. Get something like that. Okay. I'll put some data points. And then, if I were to extrapolate here, I'll get the same minus 273.13. Then I'll ask you some few questions that will get your brains thinking. If I were to measure this thing with a volume that's twice as big or half as small, how would it affect the data? Would I still get minus 273.13 as the absolute 0? Yes, I know that. Moving right on. So that's it. Boy's law procedure. Okay, all right. So anyway, here's the deal. When you actually connect the pressure sensor, be careful about this here. Make sure that you're connecting the temperature sensor and the pressure sensor to the chemistry sensor, and not the not taking the temperature sensor and plugging it here. That will kind of cause a wrinkle in the breakage somewhere up here. So make sure they're both connected to the chemistry sensor, as shown in the picture. And then here's our water bath, and we'll put a stirrer there, and then this will be heating. And then we'll program the data logger to measure temperature and pressure at 1 or 2 minute intervals or whatever it is. And it'll plot the data for us. And then we can find the equation of the line. And then we can solve the equation for that y is equal to 0 intercept. Life is good. Ha! Henry's law. In the previous version, Henry's law occurred quite early in the gas laws. Now it's kind of moved to solutions. Anyway, what's the story? The story is really simple. Pepsi. Somebody drinks this stuff. There's carbon dioxide in the headspace. This is called headspace. It's pressurized. You know that. And the point is, you would expect, and you know from everyday experience, that if we were to increase the pressure in the headspace, then more carbon dioxide would dissolve into the aqueous phase. Pressure, molarity, capital M of carbon dioxide, how are they related? One might think maybe they're directly proportional. Well, yeah, that makes sense. I double the pressure up here, I double the concentration up here. I double the concentration down here, I expect to double the pressure. That is, if you write it as an equation, carbon dioxide aqueous, that is, in moles per liter, is equal to some constant, proportionality constant, and the pressure of the carbon dioxide in the gas. So, find me the proportionality constant. So gotta find out what the pressure is and what the carbon dioxide concentration is, so on and so forth. Okay. In this case, we'll ignore the fact that that carbon dioxide exists as carbonic acid. We'll just ignore that. So how does the scheme go? It turns out it's really simple. Take your Pepsi. We're going to give you Pepsi. Nice and unopened. Make sure it's nice and dry. Wait. 3 decimal places. Don't round off. Just read what the balance says. 3. Then you're going to go. Aha! 1 or 2 seconds. Just let out. We're trying to let out the pressurized gas that's up here. Just 1 or 2 seconds. Right? Then 1, 2, and then close it. And then we're going to wait. Will the mass change? Why? What has come out? Anyway, and then after that you open it, measure the temperature of the Pepsi, right? And then you put a stir. So open it, measure the temperature of the Pepsi. Then you put a stir bar, large stir bar, stayed to degas, remove a lot of the gas of the carbon dioxide as much as possible for 10-15 minutes. And then you're gonna put in, you're gonna weigh a Mentos, 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 and then you're gonna put it in here. Weigh the Mentos and put it in here. It'll help degas. After that, you remove the stir bar. You'll measure the mass of the bottle after the degassing. Then you're gonna fill up the Pepsi with Pepsi all the way to the brim. Right? You do that, measure the mass. It turns out when you do that step, you'll find that it exceeds the mass of the balance. So what are you gonna do? Take a small beaker, put it on the balance, tear the balance, pour some of this in there, like half full or whatever it is, measure the mass of the Pepsi in the small beaker. Then you can measure the mass of this. The mass we're looking for is this mass plus the mass of the Pepsi in the beaker. All right. Then after that, what are you gonna do? Then you're gonna determine the density of the Pepsi by doing 1 milliliter, measuring the mass of 1 milliliter aliquots. You've done that many times. And then you're gonna empty the soda completely and measure the mass of the empty can. And it turns out that that's enough information to determine the Henry's Law's constant K. So let's see here. I need to open a Word document so I can show you one last thing. Where is it? Chem 1510. There it is. Almost done, my good friends. By the way, since we're in lab, don't drink the Pepsi. It might have stuff in it. I don't know. And yes, we're going to put in our goggles. We're going to put in our goggles and be safe. The lab coat, Pepsi. Anyway, it's just rules. We've got to follow the rules, even if there isn't imminent danger. Anyway, so this is the sheet here, the data sheet. Mass of unopened can, I'm calling that M1, capital M1, capital M2, and so on and so on. So you want to follow those designations because when I ask you questions down here, it's easy to do the calculation, but I want to make sure that we can check that you're doing it the right way. So, for example, if I ask you the mass of the carbon dioxide in the headspace, call it small m1, then m1 is equal to capital M1, the mass you measure first, minus m2, the mass after you let some gas out. So I want to see, I want you to, okay, see if I can find the pen. It won't let me, okay. Anyway, it won't let me. So this M1 comes from here, is equal to M1 minus M2. This comes from the data. So if the TA is coming to check, they can check this, and they won't have to check the actual numbers because they're a little difficult. And so use the designations. What is small m2? Write m2 is equal to m5 plus m6 minus m2, whatever it is. So your TA can check and verify, oh, this is what you're doing. So the rest is just data, and that makes it easier for us to work with you whenever you are off. Great lab. For this lab, you're supposed to do all the things in the lab, so come prepared. Work as a team so that you're not wasting time sitting around. I should be able to do this lab quite easily. I can do the first part, the Charles's, Boyle's, and what is it, in Monters Law in about 25 minutes working alone. So you guys should be able to do it in 50. And remember that for this lab, everything has to be handed in before you before you leave the lab. So that's a great thing. In that way, you don't have to worry about an Excel sheet or something that needs to be handed in afterwards. I like it when you work with each other in the labs and complete the exercise in the lab. Have a great day. That's your Lab 7. Thank you.